Hello everyone. In this video we're going to go over part 2 of the base and arithmetic exercises. So first we're going to go with question 5 where we're doing arithmetic of binary numbers. So we're trying to add 1101 plus 1011. So we're going to set those up on a way that we can kind of see what we're carrying. So we have one, maybe I should do it a little bit more below. Okay, here. Yeah, 1101 plus 1011. Okay, so we're gonna go digit with digit. One with one will be 2 because this is base 2 is gonna be 0, and we're gonna be carrying 1. Now we have 1 plus 1, that'll be another 0, and then we carry 1. Then 1 plus 1, 0 once again, and then we carry 1 more, and then we have 1 plus 1 is 0, and then we're gonna get an extra 1 over here, so we get 1, and so we're carrying 1 also. So we get 1 here, and then we get 1 more in the next unit. So this is going to be the final result, 1100. We can kind of verify that this is exactly the number that it is if we transform everything to base 10. So if you transform this to base 10, notice that this is 1 by 2 to the 3 plus 1 by 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0. So this is really 8 plus 4 plus 0 plus 1. So we have 13. And the same way, this is going to be 11. So this is the equivalent to the sum of 13 plus 11. And so that will be 24. Now, if you check on this, this is essentially this number here is just 1 times 2 to the 4 plus 1 times 2 to the 3 and 0 the rest. So what is that? So this is 16 plus 8, which is 24. So you can realize and prove that this is true if you pass everything to base 10, and then in base 10 is the same sum, then you're going to have that your operations are good. Okay, so now let's do the next one. We have 10111 and 011101. So for this one, I'm just going to make the sum. I'm not going to make the proof. You already saw this. But I'll include the proof on the solutions, on the edited solutions that I do for the full notes. Okay, so now we have 1 plus 1 is 0. We are carrying 1. 1 with 1, 0. Once again, we carry 1. 1 with 1, 0. We get 1 and we carry 1. 1 with 1, 0. And we carry 1. 1 with 1, 0. And we carry 1. So this is going to be the final result, 100, 100. And if you check later, you can see and you attempt the proof, transforming this to decimal numbers, you're going to see that it's going to give you the same number. But now let's do the same thing, but with subtraction, just to see how the subtraction works. In sum, we carry, but you got to remember that when we're doing subtraction, what we usually do is that we borrow. So let's do 101 minus 0101. So okay, so over here 1 minus 1 of course is going to be 0, and so nothing happens there. 0 minus 0 is just 0. 1 minus 1 then is 0, and then 1 minus 0 is just going to be 1. So this is a very straightforward subtraction, and we're going to get that this is just 1,000. I didn't have to borrow or doing it in a special here. This is just to showcase how this is going to impact the subtraction. But now let's do the next one. 110th minus 0, 1, 0, 1, 1. So now notice that I don't have anything here. So it's going to be 0 minus 1, but I need to borrow. So I'm going to borrow this one here. I'm going to borrow this one from here. And so if I borrow that one, then I'm going to have 0 minus 1. But we're going to remove that from the bit. So that is going to be just simply 1. Right? And now, for the next one, I'm going to have the same situation. I'm going to have a 0 here. Did you think about it? I'm going to have a 0 here. But then I'm going to borrow 1 from here. And so if I'm borrowing 1, I'm going to have, once again, 1 over here. And I'm going to owe 1 over here. But now, if I'm owing 1, so that means that I'm going to have minus 1 minus 0. So once again, because this is going to be borrowing 1 from this one to get to even out this subtraction. So I'm going to get that 1 again. So we have the negative 1 minus this. Now, finally, at this point, we're also borrowing from this. So for this one, I'm going to have to borrow 1 once again. And so now if I borrow 1 here, this is just going to be 1 minus 1, and it's going to be 0. But once again, now I don't have anything else to borrow because I already got this one from here. So this is going to be my end result. It's going to be 0 minus 0, and it's just going to be 0. So I just get this 0, 0, 1, 1, 1. Or if you want to, you can think of this as 1, 1, 2 on base 2. Okay? Remember that we don't really have negative numbers in here. So we got to think of this as we're doing like a 10 minus 9 situation on decimals, or 10 minus the next one, the big next one on the decimal scale, minus the units. So always is going to give me a positive value. Let's go to question number 7, where we do the multiplication. All right, so now for the multiplication, it's going to be a very similar situation that when we do multiplication on base 10. So we're going to go like setting up this 1101 times 101. And so the way that we're going to do this is we're going to multiply these elements by these elements, and we're going to move rows on the next one. So for example, 1 multiplied by this, we're just going to have a copy here of this. And we have, for the next one, after we go with 0 digit, we're going to move 1 column towards the left. So we're going to have 0 multiplied by this. And now finally, we're going to do another copy of 1, 0, 1, 1 here. And then at this point, we just need to add. So we get 1, 0, 1 and 1 is 0. We carry 1. 1 and 1 is 0. We carry 1. 1 is 1 is 0. We carry 1. 1 is 1 is 0. We carry 1, and we get another 1 here. So that's going to be our multiplication here. Okay. And so once again, if you want to verify that this is the right value, you can just convert this to the numbers that are in decimal base. So for example, if I convert this to decimal base, you're going to have that this is 13. And if you convert this to decimal base, this is 5. So 13 by 5 is going to be 65. And you can also check that that's going to be true by this. Notice that this is 247. So if you convert this, this is 1 times 2 to the 8. Wait. 2 to the 7. 1, 2, 3, 4, 5. Yeah, 7. So 6. I just need 6. So 1 times 2 to the 6 plus 1 times 2 to the 0. So this is 64 plus 1, so 65. So that way we verify that our operations are good. All right, let's move on to now more operations. But now let's use representations on a bit representations for positive and negative numbers by sign magnitude, by 1 complement, and by 2 complement. All right, so if we start with representation on sign magnitude, that's just going to be the usual representation that we'll have for the binary numbers. So, but we're going to use 8 bits for this. So if we're doing 13, we're just going to have that the first one is 0, 0, 0, and then we're going to have 1, 1, 0, 1. Remember, this is 2 to the 3, 2 to the 2, 2 to the 1, and 2 to the 0. So to get 13, I'm going to have a 1 and 2 to the 3, a 1 and 2 to the 2, which is 8 plus 4, 12, minus 1 plus 1, 13. Okay? Now, if I'm representing this with the negative number, remember that what happens is that the first digit is going to mean the sign. So the zeros means here that is a positive. And if I'm going to change to a negative, then that's just going to flip the first digit to being 1. And everything else is just going to be the same. So we're going to get this. Okay. So now for 64, we have pretty much the same notion, but we're representing in 8 bits. So I'm going to actually use, this is 2 to the 7, 2 to the 6 here. We just saw that 2 to the 6 was 64. So that representation is just going to provide me with 64. And if I do minus 64, then I'll have a 1 in front. And then that's it. This is what I need. Now, minus 1, remember, minus 1 normally will be just 0, 0, 0, 1. And that's it. That will be the number that I will use to represent 1. But because we're representing minus 1, then this first digit is going to change and it's going to be a 1. Notice that I'm using the first digit, and that works because we're never really going to use the power to the 8 in here, or the power to the 7. The power to the 7 is too big. 2 to the 7 will be 128, and we're not representing really numbers that high in this case. So that's what happens with minus 128. This cannot be represented in 8-bit to complement. Well, it cannot be represented in 1 complement or in sign magnitude, since we don't have enough in here for it. But we potentially could just represent this in 2 complements. 2 complement doesn't use the sign on the first entry here. Okay. So now on 1 complement though, we have a similar representation. Remember what we're doing for this is, for example, for 13 we have the same representation. But now what we do for minus is we flip the sign of everything. So the zeros are going to be flipped to 1. And the 1s are going to be flipped to zeros. So this is my representation here from this number. If I'm going to do 64, then I'm just going to have the same number as before, right? But then if I'm going to do minus 64, that's going to flip everything else. And this will be the representation of minus 64. Just flipping the sign from everything. Now, same thing over here. 1 will be 0, 0, 0, 0, 0, 0, 0, 0, 1. But if I get minus 1, then I just flip everything in 1 complement. And all the zeros become 1. So that's the representation that we have for 1 complement. Now for 2 complement, now I'm going to start with the base number. So we have 0, 0, 0, 1, 1, 0, 1. And then what I'll do is I'm going to flip here these numbers. So this will be 1, 1, 1, 1. And then I flip all the numbers in here. So this one's become 0, this 0 becomes 1, but the last one is just gonna stay the same. Now for this one, we have 0, 1, 0, 0, and then 0, 0, 0, 0, and then minus 64. Then we're just gonna flip these numbers here, except the one that is determining the real number. So we have 1, and then this one is gonna stay the same, and then 0, 0, and 0, 0, 0, 0. So we don't flip the one that is really representing the original number. Now, note the same thing for this. 1 will be 0, 0, 0, 0, 0, 0, and then we get up to 1 here. So the representation on the 2 complement will be I'd convert everything else to 1s, but the ones that are really representing the numbers, those are not going to change. So this stays here as a 1. Okay, so that is the representation that I have for these numbers, and the sign magnitude, the 1 complement, and the 2 complement. All right, so now in question number 9, a classmate is arguing that minus 128 cannot be represented in 8-bit 2 complement because there is no 128 to negate from. Are they correct? Explain by attempting to compute the 2 complement of minus 128 starting from the bit pattern 1, 0, 0, 0, 0, 0, 0, 0. Well, what happens here is, remember that the range of 2 complements goes from minus 128 to 127. So really the number that is not being represented is 128. We cannot represent 128. Why? Because of the +1 rule. Okay? Which is the reason why the number that is always represented is always stay the same. Because what we do, remember, is we start from a number that represents. So for example, if we have the 1, 0, 0, 0, 0, 0, 0, 0, 0, that will be usually representing the 2 to the 7, so the 128. But then I attempt to flip it. So if I flip it, I'm going to get 0, 1, 1, 1, and then 1, 1, 1, 1, right? This is just flipping normally if I'll just following the rules of everything else. But remember that in the 2 complement, we'll always have to add 1, which is why most of them, they're going to keep the original number where they had the representation. But now if I flip a 1, this is just going to transition to being 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. So really, the representation of minus 128 is going to be this one by the +1 property. Okay?